This is our lecture number 7. Today we are going to see spherical distribution. Spherical distribution of black body radiation. Spherical distribution of black body radiation. This is today's article. Here you see radiant energy emitted per unit area per unit time by a black body depends on its temperature. Rate of emission per unit area or power per unit area of a surface is defined as function of wavelength lambda. That means power emitted, rate of emission is function of lambda of the emitted radiation. At low temperature, the power radiated is small and primary lies in long wavelength region. As the temperature is increased, rate of emission increases fast. See here, Lumer and Pringshin. I will write like Pringshin. These two scientists give the energy distribution of a black body and the graph I will write here. Suppose this is the graph. Here you see radiant power, and here this is the wavelength in nanometer. Here radiant power and wavelength in nanometer. Suppose I will plot graphs like this. Suppose this is the graph. This is one graph. This is second graph. This is the third graph. This is the fourth graph. Here. Here this graph, first graph, we consider wavelength is here 0. (500 nanometer), 1000 nanometer, 1500, 2000, like this. And we take temperatures. See here, these are the temperatures for this graph. We consider 5 Kelvin. This is 500,000 Kelvin. This is 4000 Kelvin. This is 3000 Kelvin. We consider here, see, that is 500. We consider this region. This region is visible region. Visible. From these curves, it is observed that, I will write here, first thing, at a given temperature, energy is not uniformly distributed. This is the first point. Energy is not uniformly distributed. Second, at a given temperature, the radiant power increases increases with increase of wavelength, reaches maximum and then decreases. That means at a given temperature energy is not uniformly distributed, and at a given temperature the radiant power increases with increase in wavelength and reaches maximum and then decreases. Third point, area under the curve. Area under the curve represents total energy emitted per unit time, per unit area of a black body at the wavelength. Fourth, the peak of the curves shifts towards left, and that is lambda max decreases with increase in temperature. Fifth point, at high temperature total energy, that is area under curve increases. This is all about spherical distribution of black body radiation. Now we consider next article, Wien's displacement law. See here, Wien's displacement law. First we will see the statement of Wien's displacement law. Wavelength for which emissive power of a black body is maximum is inversely proportional to the absolute temperature of the black body. This is the statement. Wavelength for which emissive power of a black body is maximum is inversely proportional to the absolute temperature of the black body. That means lambda max is proportional to 1 upon T, or lambda max is equal to B upon capital T, or lambda max into capital T is equal to B, where B is Wien's constant, and value of B is equal to 2.897 into 10 raised to minus 3 mK. This law is useful to determine the temperature of stars, sun, moon, etc. By using this law, we can find out the temperatures of distant stars, sun, moon, etc. I hope you all understand this. Now we can see the next article and last article of this topic. Stephens Boltzmann law of radiation. Stephens Boltzmann law of this radiation. First we will see statement. The radiant energy, I will write here, the radiant energy emitted per unit time per unit area of a perfectly black body is directly proportional to the fourth power of its absolute temperature. Fourth power of its absolute temperature. Suppose you consider R, quantity of heat emitted per unit time per unit area of a perfectly black body, and T be the temperature. Then I can write here R proportional to T raised to 4, or R is equal to sigma T raised to 4, where sigma is Stephens constant, which is equal to, I can write here, 5.67 into 10 raised to minus 8 joule per meter square second K raised to 4, which is equal to 5.67 into 10 raised to minus 5 erg per cm square second K raised to 4, which is equal to 5.67 into 10 raised to minus 8 joule per second, means I can write watt per meter square K raised to 4. And this we consider, this is equation 1. This equation 1 can also be written as, for perfectly black body, EB is equal to sigma T raised to 4. Suppose this equation number 2. And for ordinary body, ordinary body R equal to A into EB, and therefore R is equal to A sigma T raised to 4, or R is equal to E sigma T raised to 4, because from Kirchhoff's law A equal to E, we can write like this, equation number 3 and equation number 4, since A equal to E. Now suppose you consider T, temperature of black body, T0, temperature of surrounding, then rate of loss of heat R can be written like this, R equal to sigma T raised to 4 minus T0 raised to 4. This is the rate of loss of heat per unit area, and we can write here R is equal to sigma T raised to 4 minus T0 raised to 4, or R is equal to R sigma T raised to 4 minus T0 raised to 4, this is equation number 4, or R is equal to A T raised to 4 minus T0 raised to 4, like this, equation number 5. And this is all about Stephens-Boltzmann law of radiation. Here we completed third topic, that is kinetic theory of gases and radiation. In next period we are going to see some examples on this. Thank you.